you get a 50-50 chance. T's either 1 or -1 though, at least we limit it down. We've what? Narrowed it down to 2 options. So when we know something, T has to be 1 or -1. But to know for sure, let's set the 2 equal to this original 2 plus 3L2. And then you can help me solve that. So in the T value, this is equal to this, solve for T. Well, it's 1 or -1. Which one is it? Let's find out. 2 plus 3L and a T must be equal to a what? 2. That's the dx is equal to each other.
You can't put a negative number in a log.
It's a great observation. What Sean is saying now when she goes, don't waste your time here, because she knows you can't put a negative number into a natural log, it's undefined. So it must be T equal to 1. So Sean, I love it. I'll keep working the math here, but she's saying if you don't want to waste your time here, she investigated that natural log of T, and she's saying you can't get the natural log of a negative value. Right? It's not in the domain, so it's got to be T equal to 1. Now in this problem, T equals 1, but I'll keep solving this in case someone took this route. 3 on a T equals 0. Natural log of what is 0? I'll divide a 3 on both sides, so natural log of T equals 0. T equals 1. We found it. But better than this, Sean, I agree with your observation, just saying, well, T has to be positive. So on what number are we plugging in here? We're going to do this at, I'll drop a vertical line here. At what point? At T equal to 1. Hey, by the way, in this course, with parametric curves, and in Calc 3, if you ever get stumped on this, I do want to point out T is usually something really simple, like 0, 1, or 2. Do you remember that? It's not something trying to freak you out, like T is equal to 35 over 7. They're usually giving you a simple point, like T equals 0, T equals 1, or T equals 2. In this case, T equals what? T equals 1. Same thing though. You can imagine how many times this is the thing that stumps someone on a Calc 3 test. They got everything right, but they got stuck trying to find it. Because it's this idea of parametric versus Cartesian. Parametric versus Cartesian. And we got to get those, combine those, understand those in terms of how they relate to each other. All right, let's plug this in, everyone. What's 2 times 1 over 3 over 1? What's the slope?
2/3.
There you go. And you believe the answer just like that on a test. Because it didn't say you had to solve for y, right? That's the equation of the tangent line. Unless you want to make it y equals mx plus b. Do you like to do that? There's nothing wrong with that. Well, there's one danger. What if I distribute, make a math error? Then I lose. You know this, right? So, oh, wait, look, that's the equation of the tangent line. Is that okay? Man, you all are awesome. Keep in mind, you could have eliminated the parameter and then just dealt that with everything in y's and x's. I've seen that happen before. Am I okay on this stuff? This is the stumper, though. How they don't give you T. They never mention what T does. T was in this problem.
I'm just trying to remember back in calculus that all a slope is a derivative is a slope. So you're using
right.
the T as to solve the slope, basically.
We should take time just to talk about that. Any curve, a tangent line to the curve, the slope of the tangent line to the curve is just the first derivative. The second derivative deals with concavity, and we're going to do that now. And when second derivative deals with concavity, when is it second derivative positive, and when is second derivative negative? Remember that? We can put that in the board, because we got first derivative, and we're going to have to come up with an equation for second derivative. It's not going to be hard, it's going to be this simple. How I just divided t's here, dt, okay? First derivative deals with slope, a tangent line to a curve, rate of change. What does second derivative deal with? Concavity, right? All right, I'm gonna go like that. Is that, that's a portion of a curve. Is that concave up or concave down?
Concave up.
So you can put CU for concave up, or you can put the word cup, because concave up, it looks like a cup. Does that help? Hey, when it's concave up, what do you know about second derivative? Second derivative of the function would be positive or negative? Positive. Very good. So I'm just going to put it up. Double prime is always positive. And what if it's concave down, like an upside down frown? You can just put CD. Concave down like an upside down frown. Look. Because it's upside down frown, right? Concave down, second derivative is what? is going to be negative. Okay. And then what do you call the point between a curve when it goes from concave up to concave down? Point of inflection. You all are awesome. Point of inflection. So you get the curve and went like, you know, y equals x cubed does this. Whoop. And then it goes whoop. But right there they call that a point of inflection because it changed from concave down to concave up. But we got to invent a formula for this. It's already solved this. I'm going to leave this up here. That's slope. That's first derivative. Super job, everyone. Don't let that t value stump you. What's t? What's t? I don't know what t is. Just like you suggested, just plug in and look at the original, right? So Adam, you made that so you go look at the original expression of what x and y is in the curve, set it equal to the point, whichever one's easier to work with to find that t value. And in the end, when t is like a 0 or 1 or 2. All right, second derivative. What is some notation we use for second derivative? That's one, right? Well, this is the funny one, and I'm going to start with that. Isn't that the second derivative of y with respect to x? Okay, we need to make meaning out of that so we can do this. We are trying to create a formula that we can use for finding second derivative with parametric curves. To put our t's in there. And by the way, everyone, all I'm going to do is something similar to this. I'm going to do the same thing.
Sorry, does it have to be exactly like that, so d squared y, or can it be y squared?
It's always d squared y, the notation they write. Very good question, Nicholas. That's how they write it. But listen, you probably know, don't we always just kind of go like that?
Yeah.
Second. I think that's important we see this now so we can know how to put the t's in there. This really means, what does this mean? This means I took the derivative of this. I want you to see that. I just took the derivative of dy dx with respect to x. So would you write that? When I was a student, I kept seeing this notation, Nicholas. I'm like, okay, I'll just remember that means second derivative. I put the squared there rather than here. But I really didn't understand why I was doing that until one day I stumbled upon this and said, oh my gosh, that's what this is. Look, how many d's you got? Count them. D squared, you see? We're going to take the derivative of the dy dx. We're going to take the derivative of this with respect to what letter? Yeah, keep it simple. You'll just keep saying it over and over yourself. Oh, this makes sense to me. And look how many dx's you got. Squared. And you got two d's there. That's why they use this notation. So let me say it again. You go, what is this? I'm taking the derivative of this with respect to letter x. So, are you ready to invent our formula? Was everyone okay with that move, though? All I need to do, I'm going to change colors, is divide a dt and a dt. Right here, ready? Psh, ding. And here, psh. There's our formula. That's our formula that we're going to do. We'll take the derivative of dy dx with respect to t and divide it by the derivative of x with respect to t. And I say we use the last curve. And when we're done, we can talk about where's the function, where's the curve concave up and where's the curve concave down. Does that sound cool?
Where's it sad and where's it happy?
Yeah, there you go. Upside down frown, concave down. Second derivative is negative. I gotta rewrite this. What was x again? We used the same curve. What was x?
2 plus 3 natural log t.
Ooh. What was y?
T squared plus 6.
E squared plus 6. Okay. Let's find the second derivative. Well, didn't we already find that? I'm going to write that down. What was dx dt? Or excuse me, we already found dy dx. What was dy dx? In terms of t?
2/3.
2/3. But before we put the t in there, though, we'll just find it for general for any point.
2t over 3 over t.
Okay, so it's the 2t over the
3 over t.
Hey, you want to make that look better?
2t.
Before I left it like this, and then we plugged in once, but how do you divide fractions?
Flip it.
You multiply the reciprocal. What's t 3 over t flipped over? So I get 2t over 1 times a t over 3 gives me,
2t squared over 3.
if you wanted to write it a little prettier. So that's going to go in the denominator. Or excuse me, that's going to go here. I apologize. And then we got to take the derivative of this with respect to what letter? T. That'll go up here. And then what will be in the bottom?
Dx, so it would be 3 over t.
So this won't be confusing. I think the hardest thing is just knowing this math formula. Right? How can I find this when everything's at t's? I'm just taking my Calc 1 equation and dividing dt into dt here. That's all. Alright, so what's the derivative of this? Right here, I'll put a box on it with respect to t. What's that derivative with respect to t?
4t over 3.
4t over 3. So far, so good? Nicholas, okay with that?
Yeah, what did you have? I'm just confused how you got 14 with 2.
Oh, so what we did was I took the derivative with respect to t of the dy dx we had previously, which was this. I thought we'd clean it up because I didn't feel like doing quotient rule there. You see that? I was like, wait, we can write that like this. And then we wouldn't have to do quotient rule. Now, gosh, we didn't need all this room. What's the derivative of x with respect to t? I think we already found that. That's just what? What's the derivative of x with respect to a t?
Oh, 3 over t.
There we go. Now we're not gonna write it like that in the back of the book because that's a complex fraction, right? So can we simplify that?
4t squared over 9.
Here we go. And we just multiply the reciprocal. You might think the t's cancel here, but they don't. He says you multiply a t over a 3, and you get 4t squared over 9. There's the answer. But I would like us to investigate, where is this curve concave up and where is it concave down? Cool. It's concave down when this is negative. The curve is concave up when this is positive. It may sound like a trick question though, because a lot of you are investigating right now.
It's squared.
It's squared. This is the second derivative. And second derivative, when it's negative, it's concave down. The curve is concave down. This curve right here. The curve is concave up when second derivative is positive. Isaac's saying, well, he's making the observation, you got a t squared in there. That means at any t value, this is going to be what? Positive. This curve is always what?
Concave up.
Always concave up. Because second derivative is always positive. Do you notice that? Notice the second derivative is always positive. So this curve right here is concave up. I'll put CU on what interval? It's concave up. I'm talking about the curve. The curve is concave up on the interval. Negative 8 about it. True? Isn't that cool?
Did you say the integral? You mean the interval?
The interval. The interval. That it's concave up and it's never concave down. You want to know? Here's an easier example of a curve that's always concave up. Think of y equals x squared. What does it do? Ooh, it's always, right? It's always concave up.
Are you gonna ask us, like, for that kind of notation on a test?
You don't have to put this notation. They call this interval notation. You could put it in set notation. Do you like the R? The funny.
Oh, yeah. But, but what about the domain of x and about the original functions?
Exactly.
Yeah.
So with the domain,
Like it doesn't exist.
we can talk about that as well now too. Natural log of t, and this is calling for all x and y, right? For t, these t values here. But we could go back. They don't ask you for the domain on these, but it's a good thing to investigate in terms of domain. She's saying t always has to be what? Because natural log of t always has to be greater than a what? A 0.
And x always has to be greater than 2, right?
That's right. And x always has to be greater than 2. But when it comes to that, you do not have to indicate that. But it's great observation when you're talking about this expression. Because the natural log having a limited domain, the same thing would happen with the square root. You know what freaks people out though? How this has a t squared and this has a t squared. So they think they made an error. That's why I chose this example. They think, wait a minute, I did a derivative of this. Why am I coming down to this? And it stays t squared. It's because everything is parametric right now. You're trying to think Cartesian there. You could go and eliminate that parameter and that's what you would see. Cool. I was trying another one. Hey, super job with that. I'll leave this up here. I mean, here's our math formulas, right? The reason I'm choosing this one because I thought somebody'd go home and try this tonight, and I didn't want to bug you. And it's not hard, but we can. It's a good problem for class. It's a good problem so I'm taking this from our homework problems. Practice problem number 13. X equals e to the t. And y equals t e to the negative. Now the first thing is, they don't ask you to get the tangent line of the curve on this problem. They just want two things. They want this, then they want this, and then they go, for what values of t is the curve concave upwards? So they want this, and then for what values t is the curve concave upward? Well, let's start here. That's not easy. And when the derivative of y with respect to t. What rule? Do you all spot it? It's not that I said it's not easy, it's not hard, but what rule do we have to apply? Chain rule's in there, very good. Overriding rule though. Product rule. Everyone see this? There's a t in front of e to the negative t. That's like an x times an e to a negative x. What rule do I have to apply? Product rule. I know. But just be careful of that. We have to do product rule. So let's just get ready. That's going to be the dy dt. So product rule. First times root of the second plus the second times root of the first, right? Alright, first, what's the derivative of the second? This is why I'm saying you need chain rule. What's the derivative of e to the negative 2? Chain rule, you get negative e to the negative t. So I'll put a parentheses because it's multiplication. First times root of the second plus the second times root of the first. What's the derivative of the first? That's the, oh, by the way, I should underline these because we're doing product rule here. Your first and your second. First times root of the second plus the second times root of the first, which is just a 1. A 1. By the way, I should rewrite that. What is that? Negative t e to the negative t plus e to the negative t. If anybody wants to factor, what could you factor out of that?
E to the negative t.
Yeah, exactly. What's this?
Just e to the t.
Wait. And when you said I could factor out an e negative t out of that, right?
Yep.
I think it would look cool. Then you'd have a negative t plus 1?
Yep.
Or what's another way to say negative t plus
1
1?
minus t.
I'll write that. Well, what's still in the denominator?
E over t.
How can I make that? Like, I want to bring that upstairs.
It's negative. So it is squared.
So I subtract, right? Negative t, subtract the t makes it, I'll put it right here, e to the negative t. You can write this as 1 minus t or t minus 1. I wanted to do this with you so you didn't get bugged with this. Awesome, Connor.
What was doing the last step?
So in that last step, because these are kind of like this in there, where we subtract powers. Now you go, well, that's just 3 minus 2. I got the common base. We got the common base at e, but this was a positive. So you go, okay, ready? What's a negative t subtract a t?
Okay.
And you go, oh, it's negative 2t.
Thank you.
Great question. Yeah, you're welcome. That's what I mean. I didn't want you to go back. I know this one would look a little weird there.
working that one at home, I didn't want you to freak out on that one.
Hey, I haven't done it, but if you want to investigate it while I'm working this out, you know what you might find easier on this problem? Aren't we just trying to get this and this? You might want to try eliminating the parameter. You might find the problem actually easier. I just want to point that out. It's something just to think about. Even I'll keep working the problem, but you might go, man, I wondered if I eliminated the parameter, if this problem would have been easier. Because this got a little messy here, didn't it? It wasn't hard, but you had to be careful with product rule. You had to be careful with the chain rule right there, and then this factoring thing we're being very careful. All right, is that all right with that? But hey, some of you are looking at it right now going, can I eliminate that parameter? And I bet you can.
Do the logarithm
There you go.
rule to get rid of the e.
Yeah, and see what you get, and you might look and go, this derivative's easy in a Calc 1 class. It's just something to think about. You can always eliminate the parameter. But I didn't want you to think that's always easier. Sometimes it's harder, it makes the problem harder. Sometimes a problem like this makes it easier. At least I thought it was. All right, now what do I have to do? I got to take the derivative of this with respect to what? T. So in product rule, with the chain, here I go. Take the derivative of that with respect to t. First, what's the derivative of the second?
1,
1 or negative 1?
negative 1.
Okay, first time do the second, plus the second. What's the derivative of this? Chain rule. Just negative 2e to the negative 2t. I'm gonna write that again. What is all that? That's negative e to the negative 2t minus 2 e to the negative 2t plus what's negative t times a negative 2? 2t e to the negative 2t. Sound good? E to the negative 2t with a negative. I just showed this to get the negative 2 e to the negative 2t, and then I just multiplied the negative t times this and made it positive. All right, what's dx dt though? Oh, again, what's this? This is just what? What's your next? I'll put it in. But I was hoping you can help me simplify it. Just to make it a little bit more simple, so we can look at concavity. So can I factor anything out of the top? E to the 2t, negative, right? Yeah, all right. I'll factor out an e to the negative 2t. What are we left with? That would be a negative 1 minus 2. Oh, wow, those are like terms. Plus, what's this? 2t, and what's this all over? E to t. So far, so good. You could have combined these first. Does anyone see the like terms? Yeah, very good. So now I have, oh, I want to bring that up again. Connor, if you don't mind, I'll wait till you're done writing. I was wondering if you could help me get that up here by that subtraction of powers.
It's just e to negative, or yeah, e to negative t.
E to the negative, ready? We got to do negative 2t subtract another t. So that's like negative 2 minus 1. Isn't that negative 3 now? There we go. So here it is. E to the negative 3t. This is the second derivative with respect to t. 2t minus 3. There we go. And then I was wondering if you could help me with concave up and concave down. Sean hit a good point earlier about domain. You should think of the domain of the curve. There's no natural logs in here, and everyone, domain of e to t exists for all t values, right? T can be negative or positive, so we're safe there. Concavity should be okay on this. Everyone, can you, there's a number here. Keep in mind, e to the anything is never 0. So can you help me figure out when this turns into 0? And then we can figure out when it's concave up and when it's concave down. 2t minus 3. What makes 2t minus, what t value makes 2t minus 3 equal 0?
3 halves.
3 halves, okay, so at t equal to 3 halves, right? Like a point of inflection. point of inflection. When is this curve concave up? So the curve is, and when I'm talking about this curve right here, way up here, that curve is concave up on what interval? What interval will it be? So we know that 3/2 makes it 0. When you put numbers bigger than 3/2, does this become positive or negative? This can never be 0 and this can never be negative. If you have to, make a little number line. Just help you out with it.
3 positive.
I'll just put a little number line here. 3/2, right? That's like our key point, possible point of inflection. How about numbers higher than that? Is this positive or negative? Okay, put 100 in there.
Positive.
It's positive, put a plus. What about on this side? What's the number less than 3/2 that's easy to test?
1.
I like it, 0. Put a 0 in there. 2 times 0 minus 3 is what? This is going to be concave down over here, and then it's going to be concave up over here. And it looks like at t equal to 3/2, we have a POI, a point of inflection, or an inflection point. So when it's concave up on, I'll use interval notation, 3/2 to infinity, and where is it concave down? CD.
Negative to negative 3/2.
And I do want to go back to Sean's good point about, well, we should investigate domain. Now we wrote that. Is this function okay in terms of domain? We're like, well, it has e to t, we're safe. E to t there. The only thing is, yeah, e to t can never be 0, so we don't even have a problem with like the denominator. There you go. Hey, now that we did all that, there was a lot of writing on the board. I was wondering if someone knew how to eliminate the parameter. Because you might have found this problem, I don't know.
Natural log of x.
You eliminate the parameter just for fun, just for kicks. Plus, by doing this helps you better relate Cartesian and parametric. The idea of looking at curves parametrically or just Cartesian. So, what would t equal to here?
Natural log of x.
Okay, so I'm going to write that down. T equals the natural log of x if x equals e to t. Take the natural log of both sides, right? Natural log of x would equal natural log of e to t. T equals natural log of x. Is everyone okay with that? Where could I substitute that? Here's your curve. Y equals natural log of x times e to the negative what? I bet you we can make that simple. Where can I move that little negative? Properties of logs. Right there? So I'll write this again, everyone. This is equal to natural log of x times e to the natural log of x to a negative 1. What's e to the ln of x? So close.
Parentheses.
E to the ln of blah is blah.
Yeah.
So what's e to the ln of x?
X.
So we have an x to the negative 1. This curve is y equal to natural log of x times x to a negative 1. And what is x to a negative 1? 1 over x. So my point is, I'm going to put it right here when I got enough room. This is the curve. Can anyone see that? That's the curve we're talking about. That's the same curve as this goofy stuff right here, which looks confusing. It's just natural log of x over x. Okay, you do a derivative, you got to do what? Quotient rule and stuff, unless you want to do product rule. But you might have found it easier than this because we still have to do product rule, right? I just want to point that out. Sometimes you can look at it. This problem didn't say anything about eliminating the parameter. They just said find dy dx and find the second derivative as well. So I just want to point that out. Sometimes you eliminate a parameter. You might find this easier to work with than this. But now, hey, going back to domain, I know these were t values, but x, right? Natural log of x, so like, wait a minute, x here would have to be greater than 0. I know. Hey, can I raise?
How did the x? How was the x the negative first time?
Oh, so e to the ln of what? Blah. It's just blah. So e to the ln of x is x. This was all raised to a negative 1. So I replaced that with x, which was now to a negative 1. Do you see that? And the first thing I did was I took that negative 1 there and I moved it to this power here, which is one of the properties of logarithms. Cool. And by the way, that would always happen. Here's another one. E to the negative 5 natural log of x. Let's look at that. Just for another example. I can move this where? Here, you get e to the natural log of x raised to the what? Negative fifth, but what's e to the element of x? X, you get x to the negative fifth. Or 1 over x to the fifth. Isn't that cool? Now what if this wasn't negative? Can we do one of those? You might find it easier. You want to simplify that? E to the 5 element of x. Oh, wait till you got this.
Ends up being x to the fifth.
Yeah. You might find that one a lot easier. E to the 5 element of x. Okay. Hey, you might find this one easier. I can do that one. Boom. Here, it's just going to be what? X to the 5. Okay, cool. But the negative can throw you off if that's what's happening there. Nicholas?
So how do we relate the answer that we got e to the negative 3t to the 1 element x squared?
Wait, say again?
So this answer that we got, we eliminated the parameter.
Right, and I want to point some stuff out. We got a lot around the board. This, Nicholas, this was the first derivative. So I'm going to put a word here. This would be slope of curve. The curve was just defined parametrically. That's the slope of the curve. But you know, this is, we've eliminated t. If you took the derivative of y with respect to an x, which you notice you could do quotient rule, it wouldn't be that bad though, would it? It's not that bad. You're getting the slope of the curve.
So that's just in terms of t.
That's right.
Okay.
That's all, exactly. And I didn't want you to like, is this better? See, it's hard to see now the need for this. It's like, it's not that it's better or anything. You're just getting used to putting things, what, working parametrically with curves. But there becomes a need, like in Calc 3, when we want to do everything parametrically. Cool. But then, hey, this answer, right here, this was second derivative. That would have been like you get the second derivative of this, which deals with the concavity. I love it.
But if, wasn't the question to find at like the point of, explain, point of inflection? And it, was it not? What was
No, they just said, but I know, they just wrote for which values of t is the curve concave upward.
that?
But you're right, you know, that concave upward, concave downward does deal with a point of inflection, but that's all they asked, so we didn't have to list that. And I love your question. Yeah, when the book on this one, they just go, what values of t is the curve concave upward?
So can we go from that final equation of t to the point of inflection, or where we have?
You sure could.
Yeah.
I love it. She goes, t would equal 3 halves. And at t equal to 3 halves, I'm going to write this here, Sean. At t equal to 3 halves, concavity of curve, because the curve is the curve. Concavity of curve changes. And what I mean by changes, it changes signs. Everyone, it goes from concave down to concave up. And by that, the definition, at that value, that's the point of inflection. But to find it in x's and y's, what would you have to do? Plug it in here. But hey, what's the point? E to the 3 halves, comma, 3 halves